Hello, once again. Okay, so as we studied the abstract in earlier lecture, so it basically giving an idea that our reflective, intelligent reflective surface having a discrete phase shift constraint. So our problem is believed as difficult because it is not linked with any combinational problem. Okay, so if it is related to any combinational problem, so we can solve efficiently. There's the two algorithm like branch and bound algorithm and approximation algorithm, which constitute the best result in this area. Okay. Nevertheless, this work shows that a global optimum can be actually be reached in linear time on an average for the number of reflective elements. The main idea is a geometrically interpretation of the discrete beamforming problem by choosing the optimal point on the unit circle. So in this lecture, we have shift from the theoretical things to geometrical things. Okay. So main idea that we have to interpret the geometrical thing of a discrete beamforming by choosing the optimal point on the unit circle. Okay. All the number of possible combinations for the phase grow exponentially with the number of all the reflective elements. Okay. It's turned out that there are the only linear number of circular arcs that can possibly contain the optimal. So there is a few of only limited things of few limited point on the unit circle can be considered as an optimal point. Okay. Furthermore, the proposed algorithm can be viewed as a novel approach to a special case for the discrete quadratic problem. Okay. So when further we propose different algorithm and can be viewed as a novel approach to that special case of a discrete quadratic program. Okay, the index term. So index term that are we using in this is that discrete beam forming for the IRS or IRS. So intelligent reflective surface or RIS stands for the reconfigurable intelligent surface. Okay, and global optimum, that's the final optimal answer, is termed as a global optimum. Linear time algorithm is simply saying trying to say that is order of n. Okay, and a discrete quadratic program, that is it is special case, it is a special case, so it stands for the QP, quadratic program. So let's see what try to show or try to explain. So first is the introduction. Okay, so reconfiguration intelligent reflective surface concerned with the choice of best phase shift across the reflective element. Hmm. So reconfiguring the intelligent reflective surface is a concern because we have to choose the best phase shift across all the reflective elements, and mainly namely passive beam forming is two-type beam forming is active and passive one. Active one, it automatically adjusts their phase for the all the reflective element, but passive it is we have to decide which is the best to boost the signal reception at the target receiver. Okay, so by knowing that, the basic gist of this paper is simply we are reconfiguring the intelligent reflective surface by choosing the best phase shift across all the reflective element so that the beam forming uh, boost the signal reception at the target receiver. The existing study area mainly divided in two categories. Okay, so these assume continuous phase shift to ease optimization or analysis, and those restricting the phase shift to a given discrete set of practical standpoint. So in this point, it's explaining that our studies are mainly divided into two categories. Okay, our study divided into movement category and assuming the phase shift to a ease optimization by analyzing, and those restricting the phase shift to a given discrete set from the practical standpoint. Okay, this work this work belongs to a latter. This work belongs to a latter, and we establish a result that seemed at first surprising. The discrete IRS being problem has a order n algorithm for this solution, and here n stand for the number of reflecting elements. Okay, so in this paragraph we simply understand that for the reconfiguration of intelligent surface, we choosing the best phase shift across all the reflective elements. That is its passive one, through which we can boost the signal as the reception for the target receiver. Uh, we have we have existing two areas, mainly divided into two categories. Those assuming the continuous phase shift for each computation, or analyzing those restricting phase one. So like this one, omega, 2 omega, 3 omega, 4 omega, like that. And another thing we have to the restricting phase shift. Also we have to notice why we not selecting that phase shift, and why that's become what we called, it's become a very tedious for us to compute. Okay, so this work belong to a letter, and we established that a surprising thing is happen is that in previous paper we see that beamforming can take an exponential time complexity, but in this IRS beamforming problem, it can be done into the order of an algorithm for the best solution. So here n stand for the number of reflective element. Okay. After that, the proposed algorithm scheme for the geometric interpretation. So proposed algorithm scheme for the geometrical interpretation of the IRS beamforming problem, which was the first proposed in paper 3, while paper 3 focused on binary beamforming case with each phase shift belong to either 0 or pi. So in previous paper we can see that the paper focus on the binary beamforming case, where we have to either choose the value of a shift will either 0 or pi, and this work go further and account for the k array case, where each phase shift k further in that paper. The second part is the k array case, where each phase shift can take k discrete value. Okay, so instead of the binary shift keying, in which we use only two value for the phase shift, either you choose 0 or pi, but in the k array things we have to choose the phase shift value in a k discrete value. So we propose visualization of each possible solution as a point on the unit circle. So we propose a visualization of each possible solution as a point on the unit circle. The point moving on the unit circle captures the total beamforming decision. The point moving, that is the point we are moving on the unit circle, uh, capturing the different beamforming decision. Okay, that is essential. So on a unit circle capture the different beamforming decision. Okay, the essential power of the above geometric method arise from the following observation. So essential power of the above geometric methods arise from the following observation. What are these? All the number of possible for the phase shift grow exponential with the number of reflective elements. Okay, although the number we can expect that it can grow exponential with as we increase the number of reflective element, but there was a most there are the at most a linear number of unit circle arc that possibly contain the point of optimal beamforming. So we simply trying to plot all the possible k discrete phase on the unit circle, and this the choice number of possible combination are lies on the unit circle, and it might go to the exponential things, but we know that there are at most linear number of unit circle a linear number of unit circle arc that can possibly contain the point of optimal beamforming. Okay, Furthermore, the utilities of all these are can be computed. Although the utility of all these are can be computed in a linear time. Okay, and the main idea behind the proposed algorithm is to try out all the possible arc, and pick the best, and then recover the optimal phase shift. So why we are trying the arc things like geometrical interpretation things, that because using the arc for computing in the linear time. The main idea behind the proposed algorithm is to try out all the possible arc and pick the best and recover the optimal phase shift. Okay, so let's can we scheme through all these paragraphs. So in first paragraph we understand what we are doing. We are just selecting the best phase shift for all our reflecting element, and we have namely massive beam forming. We have to boost the signal to the receiver end. The existing studies are mainly divided into the continuous phase shift for the ease computation, or analyzing the restricted phase shift. Why we are not selecting that point. The work belonged to the latter, and we established a result that is surprising order of and complexity. And the proposed algorithm stem from a geometrical interpretation of the IRS beam problem, and we propose in paper number 3. While in paper number 3 we also discussed the binary beam forming. So either we select the phase shift as a 0 or pi, and further we move for the k array case, in which phase shift k can take k discrete values, and we propose the visualization for each possible solution on the unit circle, and moving around the unit circle capture the beam forming decision. Okay, the essential power of geometric method arise because, as we see through our observation, all the possible combination of phase shift can grow exponentially with the number is simply when we increase the of number of reflective elements. At most at most the linear number of point on the circular arc that possibly contain the point of optimal. So we can see that not all the points, only the linear number of arc who are giving the best and optimal answer. Okay, the furthermore the utility of that arc can computed in the linear time. The main idea behind the proposed algorithm is to try all the possible arc and pick the best one and recover the optimal phase shift. Okay, and the existing work, let's see what we have to select. That's a blue one. So these existing work seldom considered as a global optimum for the discrete IRS beamforming. Although the IRS technology has been extensively studied over the past few years for many complicated system model, the simplest point-to-point model is still far less well understood. Okay, the existing work for one the IRS beamforming. Although IRS technology has been extensively studied over the past many years, and over the complicated model, the simplest point-to-point model is still far less understand. Okay, a common practice in this paper, yeah, in this literature, we can say, is the first solve the relaxed continuous beamforming problem via standard optimization, and then round the solution to the discrete sets. Okay, so we are not simply jump on the direct problem. We simply first go on the relaxed continuous beamforming by the standard optimization technique. Then after we round to the solution for the discrete set. Okay, like an example, paper number 2 and paper number 5, paper number 4 and paper number 5, based on the semi-definite relaxation. So that stands for the SDR, and based on the minorization and the maximization, that is for the relaxed continuous beam forming problem. Okay, enforce the discrete constraint by penalizing, but resulting a non-convex problem is still difficult to deal with. Okay, so as we said that the existing work on this IRS system is still going on, and this technology is studied over many of the years, in the past many years, and it is on the different complicated system model. The main point-to-point model is still less understand or less understood by anyone. But the common practice in this literature is to solve the common practice in this literature is to solve in a relaxed continuous beamforming problem via a standardization optimization technique, then round the solution in discrete set that we earlier see in the paper number 4 and paper number 5, which based on the SDR, that is stand for the semi-definite realization, and the 6-7 paper or 6 and paper explain the minorization and the maximization things. Okay, for the relaxed continuous beamforming problem, enforce this relaxed continuous beamforming problem enforce the discrete constant by penalizing, but resulting in the non-convex problem is still difficult to deal with. And another popular idea in paper 9 and paper 10 is decide the phase shift. Another popular idea in paper 9 we can see to decide the phase shift of one reflective element at a time, but the performance of such a greedy search is not provable. Okay, the phase shift of one reflective element at a time, but the performance for the such greedy search is not provable. Okay, some other work in paper 11 and paper 12, paper 11 and paper 12 exhort the branch and bound algorithm obtain the global. So in paper number 11 and paper number 12, it's explain the branch and bound algorithm to obtain the global optimum for the discrete IRS beamforming. But these methods are incur so in incur but these methods incur the exponential time complexity and provide a limited insight. Okay, for the practical approach, the best result so far for this literature is to attempt the approximation ratio for the global optimum that we study in paper number 10. Give the approximation ratio of cos squared pi optimal signal to noise ratio. Okay, where k is number of different value of each k. So k stand here is a number of different value for the each page shift can take, like in graph we can say the plotting on the x-axis, the k can take value 2 to 12. Okay, and we further move in a paper number 3, we can see that it's 0.5, yeah, 0.5 pi k. More 14, consider the discrete IRS beamforming in the absence of channel information. To the best of our knowledge, the present work gives the first polynomial term algorithm for the discrete IRS constraint by penalizing, but resulting in the non-convex problem, but still not dealt by the many of the researchers and the phase shift. Another popular idea in paper 10 or paper 9 is to decide the phase shift of each reflective element at a time. Okay, which is best, but for the performance of such greedy search is not provable. Okay, so we move to the another paper 10, 11 and 12, where we use the branch and bound algorithm to finding the global optimum for the discrete IRS beamforming. But these methods incur the exponential time complexity and provide a limited insight. For the practical approach, the best result for this for this literature is attain approximation ratio of the global optimum in we see in the paper, that is cos square pi k in the term of the global optimal signal to noise ratio. Whereas we have to show what is k. K is a discrete different value for the phase shift, and we further move in a paper, we can see that it's the approximation ratio is 0.5 plus 0.5 cos pi by k. Moreover, in paper 13 and 14, consider the discrete IRS beamforming in the absence of channel information. Consider discrete absence of channel information. To best of our knowledge, the present work gave the first polynomial time complex time algorithm for discrete IRS beamforming with the probable global optimality. Okay, till now we have studied all the things. So in next lecture we continue from here. So